In the last video, or actually the last two videos, we had talked about resonance of carboxylic acids. In this video, we're going to talk about resonance of amides. Now, before we do, let's just briefly talk about amines. Remember, amines have this general structure, a nitrogen atom, two hydrogens connected to some other group, whatever it may be. Now, here in this situation, this nitrogen is sp3 hybridized, and we can see that by considering the orbital block diagram for nitrogen. Nitrogen is like this, and then 3 electrons, 1 each, and the 2p orbitals. And then what happens is all of these, the s orbital and the 3p orbitals, all of them combine together to give the equivalent, the equivalent sp3 orbitals. We say equivalent, we mean energy-wise. And we combine together here 4 atomic orbitals. What comes out, of course, is 4 sp3 molecular orbitals. And again, a single electron, and then one of them will have a paired share of electrons. So this can form a bond, this can form a bond, this can form a bond, and then we have this lone electron pair. And remember that the geometry here is a tetrahedron. So we have the nitrogen atom, then surrounding it would be the tetrahedral structure. This would be part of the tetrahedron, this would, and then we have these sp3 unshared electron pairs. And again, those are sp3 electrons. So that's the basic structure of an amine, and having these lone electron pair available means that it can hook up to a proton, so amines are fairly basic by nature. Now, let's compare and contrast amines with amides. With amides, we have this kind of structure. Just drawing a generic one. Carboxyl group, or a carbonyl, connected to some functional group. And then here we have, again, nitrogen with 2 hydrogens. But what is different for the amide, what makes all the world of difference in the properties of this nitrogen versus an amine, is this nitrogen is sp2 hybridized. Now remember from video 8, the carbonyl oxygen, this too is sp2 hybridized, and this has 2 unshared pair of electrons. And as you saw in video 8, these are sp2 electrons. Now, for the nitrogen, going back to the block diagram, the orbital block diagram, the 2s and the 2p orbitals, there's the orbital block diagram for nitrogen. What happens is one of the s electrons gets promoted to the p orbital, say like this, and then pairs up with one of these p electrons. Now it takes energy to promote from the 2s orbital to the 2p orbital, and further, now we have the shared pair of electrons. That this is less energetic stable than when we had it before, when we had lone electron pairs in all three p orbitals. So going from here to here does require some energy, but the reason why it's done is because we go back to here. First of all, what it means is these hybridize 1s and 2p orbitals to give 3 molecular energy equivalent sp2 orbitals. And this p orbital was unhybridized with the electron pair. So these all have a single electron. So the nitrogen can form 3 sigma bonds. Here, here, and here, just like it did for the amine. What's different is, of course, these are spread apart 120 degrees now. It's a different geometry. But here then, the unshared pair of electrons, these are p orbital electrons. So if the nitrogen is here, we have an sp2 orbital, an sp2 orbital, an sp2 orbital, each containing a single electron. And then one of these overlaps to form the carbon bond. The other two overlap to form the hydrogen bond. But now perpendicular to it is the p orbital with this unshared pair of electrons, these pi electrons. And those we are designating right here. So those are pi electrons. The advantage of having it like this, instead of having this sp3 hybridized, is that now we're set up for an electron delocalization resonance type situation. So that's why with amides, the nitrogen is sp2 hybridized to give us this p orbital or pi lone electron pair. So that now you can see that we are set up to generate some resonance structures like this. Let's just draw this down here. Like this. What can happen is, as you saw us do now in the previous videos, these are pi electrons in the p orbital that's perpendicular here. Here we have a pi bond. The carbon and the oxygen both have an electron in there that they're sharing between them. And remember, this oxygen is sp2 hybridized. So these lone electron pairs are sp2 electrons. Now what we imagine is this oxygen takes both electrons for itself, leaving the carbon electron deficient. But here we have these pi orbital electrons. They can move in to make the pi double bond over here. So now the structure is this. Oxygen has a negative charge because it stole an electron from carbon. Nitrogen here has a positive charge because we have this double bond, but nitrogen donated both of the electrons to form that double bond with carbon. And of course, this initially had a positive charge because its electron was stolen, but then it gets a free electron from the nitrogen, so this has no charge. So for an amide, we can have this type of resonance. Now here we have separation of charges. That's not ideal, but it is permissible. Oxygen is more electronegative than nitrogen, and the negative charge ends up on nitrogen. So this is not a bad resonance system. Also, because nitrogen, again, is not as electronegative as oxygen, when we had a carboxyl group here, it can, for the electron delocalization, the electrons are held looser by the nitrogen, so in fact you have a better resonance system compared to this. Here's carboxylic acid in protonated form, and as you saw in video number 8, we can have this kind of resonance here. We have separation of charges. An electronegative oxygen ends up with a positive charge on it, so this is not a real good resonance system, which means that the carboxylic acid is not particularly well stabilized by any resonance, therefore it's a fairly active molecule. Compare that now with amide. Here we have a separation of charges again, not particularly desirable but permissible, but the positive charge now is on nitrogen instead of oxygen. Nitrogen, of course, is less electronegative, so this is a better resonance system than this, meaning that the amide is a little bit more stable than, let's go back to here. Okay, this is our carboxylic acid, the resonance of that. Here it is for the amide. The nitrogen has a positive charge, the oxygen has a negative charge, as we just drew a few moments ago. But here, for the carboxylic acid, this oxygen has a positive charge. This is better because nitrogen, the less electronegative element, has the positive charge. And what's more, thinking now in terms of electron delocalization, for these pi orbital electrons, they're held less tightly by the nitrogen than they are here for the oxygen. We have a lone pair of pi electrons here, but the oxygen here holds these more tightly than what this nitrogen does. So overall, for the amide molecule, its resonance is a better form of resonance than for the carboxylic acid. So this is more stable, therefore it is not as reactive as this is. And as we'll see in a few minutes when we explain in more detail, that's one of the reasons why an amide is not as acidic as a carboxylic acid. We'll come back to this point in a minute. Let's examine here then, realizing that we have not too bad of a resonance system here, but let's ask the question, what happens if this loses a proton? So that here then, where we had a bond, now we have an electron pair. Before this was sharing an electron with hydrogen. The nucleus, the proton, goes away. This keeps the electron. So now we just have, and that was an sp2 bond. So here we have an sp2 electron pair, but this has a negative charge now because it kept the electron from hydrogen. Just the proton left. So what we're saying is that here we have this. Now what happens if it loses a proton? So now we have N with one hydrogen. And remember, it did have a lone pi electron up here. It still does. And now it will also have lone sp2 electron pair. From this hydrogen left away and left its electron behind. And this has a negative charge. We'll just say minus H plus. Okay, so now we have an anion here. What is the resonance stabilization of this compared to the amide when nitrogen kept both protons? Let's examine that. So here we have remember, the carbonyl oxygen has two sp2 electrons. Now we have the nitrogen with a negative charge. It has two unshared pair of electrons, an sp2 and a pi lone pair, and it's the p orbital pi lone. It's the p orbital lone electron pair here that we're interested in, because here's where we can get the electron delocalization as we demonstrated in our previous videos. So we get this. Now we're drawing resonance structures. Here again we have the pi bond, and you can imagine it going like this. The oxygen keeps both of the pi electrons, leaving carbon deficient, but then these pair of pi electrons come in, so we have it like this. Oxygen has a negative charge because it's stolen an electron from carbon. We have a double bond here. And because this donated both electrons to form the double bond, that would give this a positive charge, but it had a negative charge to begin with because it lost a proton, so this has no charge on it. So, looking at this resonance, here then we have no charge separation, like we had up here, so that makes it more ideal. And then here we had a negative charge, then over here the negative charge is up here, so instead on the oxygen, so instead of having charge separation, we have charge dispersion. So what this means is when the amide loses a proton to form this, you have a better resonance setup, a better resonance system than what you had when the amide was in protonated form. This is not a bad resonance, so this is somewhat stabilized, but this is a better resonance. So what it means is that amides can be acidic, and they are certainly more acidic than amines. Oops. Which are like this, but this lone electron pair, these are sp3 electrons. There's no resonance stabilization even if it does lose a proton. So the amines are not going to be acidic at all. They're going to be basic, and you have these lone electron pairs that a proton can attach to. But for the amide structure, here we see that it can lose a proton like this and have a pretty decent resonance stabilized anion that results. So therefore, amides can be somewhat acidic. Now, what about if we compare the acidity of an amide to a carboxylic acid? Let's just make some room here. And let's look at these. First, when a carboxylic acid loses its proton to form this anion, we have a very good resonance system set up, as we pointed out. I think that was in video 8. Here we have charge dispersion and we have symmetry between these two canonical forms. And again, we discussed that in more detail in video 8. When the amide loses one of its protons to form this anion, you do have a decent resonance stabilization here, but not as good as this. For one reason, when the carboxylic acid loses the proton, the negative charge is on oxygen. Here, when it loses a proton, the negative charge is on nitrogen. Nitrogen is less electronegative than oxygen, so it accommodates that negative charge not as well. So that's one reason then why the amide is less acidic compared to the carboxylic acid. The other reason is we have this symmetry in this resonance here, in these canonical forms, and that makes a particularly strong resonance system. Here, for the amide, we do not have that symmetry. It's not a bad resonance. It's better than this, so it will lose the proton, but the tendency to lose this proton here is less than the tendency to lose this proton here, again for two reasons. Number one, here the negative charge is on the electronegative oxygen. Here it's on the less electronegative nitrogen. And reason number two, this anion is much better stabilized than the amide anion. This is better than this, so amides will be somewhat acidic, but not as acidic as a carboxylic acid. And there's another reason. It goes back to what we spoke about a few minutes ago. Here, with the protonated form of the carboxylic acid, you have sort of a resonance stabilization here. It's not very good, meaning this is not particularly well stabilized, meaning it's going to be active. Here, with the protonated form of the amide, this is not a bad resonance system. It's better than this, so this is more stabilized than the protonated form of the carboxylic acid, again making it somewhat less reactive. So what we're trying to show in this video is that amides can be acidic, but they are not as acidic as a carboxylic acid. And again, there's several factors that are built in to that explanation. Okay, that's it for this video. It got to be a little bit long. Hope it was worthwhile. Come back again. We still have a little bit more to discuss concerning resonance of amide compounds. We'll do that in the next video.